So we all learn the Cartesian plane or the rectangular coordinate system. We all know, or at least I hope we do, that we can represent points on a 2D plane with an x-axis, an x-axis, and a y-axis. Right? That's how we learn, algebra. That's the first sort of coordinate plane that we use. But there are so many other ways to represent points in 2 dimensions, and the polar coordinate system is one of them. So I'll explain how this works, and hopefully remember the unit circle because that is pretty crucial to this. I have it right here, this image by USF. So basically, how the rectangular coordinate system works, right? The one that we're used to. We have an x coordinate and a y coordinate. I don't know why I erased that. And we just, whatever our coordinates are, let's say it's 3, 4, we just go that many ticks to the right for on the x-axis, however many ticks on the y-axis, and then that would be our coordinate on the rectangular plane. Yeah, the Cartesian plane. And in this way, we can represent every single point on that plane. Remember, a plane is a flat surface that extends indefinitely. So this continues infinitely, and there are infinite amount of points on a plane. But the polar coordinate system is also on the same plane. It's on a 2-dimensional plane, and we can also represent an infinite amount of points using that coordinate system. And every point that we write on the Cartesian plane or the rectangular coordinate system can be represented in the polar system and the other way around. Because the points are the same, right? They all exist, but the way we're representing them is different, okay? Like both of these were human made. This one just tends to be more commonly used, but it doesn't matter. The points are the same. It's just the way that we're representing the points is different. Okay. So how does the polar system work? Well, the way we represent a point on this plane is that we have to give it a radius and an angle, okay? So every point can be represented by an angle and a radius. What does that mean? So let's say I had this point right here, this random point, which I don't know, okay? Just a random point. And how would I represent that using the polar coordinate system? Well, I'd say that, like, if you drew a straight line from this point, okay, let's do an actual straight line. If you drew a straight line from this point to the origin, this would be a certain angle, right? And this, the actual distance, the magnitude of, the length from this point to the origin is a certain radius. So we can say that this point is a certain distance from the origin, which we say is r, and a certain angle, right, from this axis, which I think I mentioned earlier is the polar axis. So that's how we define this, okay? A certain angle away from the polar axis and a certain radius. We can define any point here like that, or if our point was just a little bit further out like here, but on the same angle, well, all we'd have to do is just increase the radius. And a lot of points are a lot more easily translated this way. Like, a common use of this is points, since the polar coordinate system is angle based. If you want to rotate a point, it is so much easier on the polar coordinate system if it's like some obscure amount of degrees rather than on the Cartesian plane. It's just so much easier. And even if you need your coordinates in xy, the xy coordinate system, it's fine, because what I like to do is I just convert my coordinates from xy to, r theta, I rotate them, and then I convert them back to xy, and I just find that super simple. So this polar system, I know a lot of people, when they learn it, they're like, oh, polars are the bane of my existence, they're so complicated. Well, the only reason we're thinking that is because we learned the Cartesian plane first. If we had learned polars first, we would think, oh, the xy plane is so complicated. So it's just a matter of practicing and getting comfortable with it. So yeah, let's practice converting some coordinates, right? Okay, let's practice that. And so usually I'm going to do examples that you can do on paper, right? But the only way we can do something like that is if we have an angle that's on the unit circle or an angle that's easy to derive using trig identities, right? So I'll just use some really basic angles and we'll go from there. Okay, so let's say we have the point. Let me bring this image down. or actually, I hope you remember this because I'm deleting it. So let's say you have the point 1 square root, yeah, let's start basic. The point 1/2 square root 3 over 2. Okay? I'm sure you all know what this point is on the unit circle, right? Because whenever we have points on the unit circle, the first coordinate is the cosine angle and the second coordinate is the sine. If you don't remember why, that's because the x distance, right? Like let's say we had this point right here. The x distance is cosine, right? It's x over, this is the radius, but it's the hypotenuse of this circle. So cosine of that angle is equal to x over h. So the x distance is the cosine, and you can say the same for y. But this coordinate is a common coordinate, and it's on the unit circle, and it's just 1/2 square root 3 over 2, which is right here, 1/2 square root 3 over 2. And as you can see, we can represent this pretty easily in radians, and because it's a unit circle, the radius is just 1. And so the angle, I like to do angles in radians. That's just more conventional, and I think it looks better. Please don't do degrees. I mean, if they ask for degrees, do degrees, but please get used to radians. So the angle is pi over 3, or 60 degrees, but remember, radians. So this is how we'd represent this. So this is xy, and this is r theta in the polar coordinate system, okay? Now, what if our xy coordinates were something like 1 square root 3? Then what? Well, if you notice, this is just 2 times 1/2 square root 3 over 2. So this is something that you'll see a lot, where you have numbers that look really familiar, whether they have 1 or square root 3 or square root 2, because there's a coordinate square root 2 over 2. And that's because they're just taking these coordinates and they're scaling them up by a certain factor. Now, what does this mean? Well, all this means is that you're taking your coordinates and you're scaling them up by a factor of 2. So now we can convert this into our polar coordinates, and we already said that it's 1 and then pi over 3. But since these coordinates are twice as big, and this is where knowledge of vectors kind of comes in, we know that the radius is not 1, but it's actually 2. And the angle is still pi over 3. The angle does not change because, like I drew for you before, it's just on that same line from the origin. So, for example, let's say we had this vector, okay? And this vector has an x component and a y component. But now we say we want to scale this vector up by a factor of 2. And you can think of this as scaling your radius up by a factor of 2. So let's say we want to scale our vector up. Now, because this hypotenuse of this triangle is twice as big, think of it as scaling this triangle up. So now the x is twice as much, and so the y is also twice as much. And that's kind of what happened here. The x coordinate and the y coordinate both were scaled up by a factor of 2, and so the radius had to be scaled up by a factor of 2, and you can think of it that way. You can see that they'll sometimes have the radius. You'll have 1/4 and square root 3 over 4. That's a little less common, but you'll definitely see this a lot. Okay, now, converting from, actually, I think there might be, another way you can do this, if you don't know the angle right off the top of your head, is use tangent. Because in the rectangular coordinate system, let's take this for example, just the same coordinate, you would have 1/2, or let's use this one, 1 to square root 3, if you drew this out. So, whenever I would recommend, whenever you're learning something new in the plane, or, I even like algebraically, I like drawing stuff out, always draw it out. So this is going to go, let's say, let's do it in a different color. So this coordinate right here is 1, this coordinate is square root 3. When we draw this out, this is our coordinate, and it makes a little triangle with our axis, right, our x-axis. And so if this is square root 3 and this is 1, and we need to find this angle, okay? It's pretty easy to find the radius. We just do Pythagorean theorem. This is 1, this is square root 3, and lo and behold, lo and behold, when we do the Pythagorean theorem, we get the square root of 1 squared plus square root 3 squared equals, square root of 4, which is 2, and we know the radius is 2. Okay? So that's how you find the radius, but the angle is a little trickier. So, all we have to do is say, this side length is square root 3, and this side length is 1. Let me erase this so it doesn't get confusing. All we have to say is that the tangent of this angle, or we could use sine and cosine now that we know the hypotenuse, but the hypotenuse isn't always going to be like the best number. Just do whatever looks the easiest to you. So the tangent of this angle, theta, is going to be square root 3 over 1, opposite over adjacent. And we know that when we take the inverse tangent of this, so we take the inverse tangent on both sides, and we get that theta equals, I would say arctangent, but I guess inverse tangent looks better, equals the inverse tangent of 3 over 1, or just square root 3, and we know that this is pi over 3. Theta equals pi over 3. So, that's how you'd find the angle if you didn't know how, or, sometimes the angle isn't a nice, pretty angle, and you'll have to put this into your calculator to find the angle. You'll see this with vectors sometimes. So that's how you convert from rectangular to polar. Polar to rectangular is, also very similar, and I'll explain it now. So, let's do a different angle. Let's say our coordinate is 5, and then how about why am I spending so long on this? Like, it's literally not a huge deal. Let's do 5, and then 4, I'm so bad at this, 5 pi over 6. There we go, I finally decided an angle. Okay, this is going to be our polar coordinate system. Remember, 5 is the radius, and this is the angle. And we want to convert this into rectangular coordinates. Okay, so first, let's draw this out. 5 pi over 6 is almost over here, right, on our little graph, because this is pi. Wow, so maybe it's a little bit more. It doesn't really matter. This is just to visualize it. But, yeah, that's 5 pi over 6, and this is 5. And so we're going to say this degree is, I don't want to write it out there. I don't think there's enough space, but that's theta. And so, we need to find the x and the y, right? X, y. They are something, which we do not know. We need to find those values. So, we can say that x equals, or x over 5 is cosine of theta, which is 5 pi over 6, right? Cosine is adjacent over hypotenuse, and so we know x over 5 is cosine 5 pi over 6, so we can say x is 5 cosine pi over 6. And so we know that sine of theta, which is 5 pi over 6, is going to be equal to y over 5. So y is equal to 5 sine pi over 6. Okay? So there we have it. Our x and our y, this is how we find them, using just normal trigonometry. It's not too bad. And if we see, we can generalize this by saying this is always going to be the radius, the hypotenuse is always going to be the radius, and we're always going to say x over the radius is going to be equal to cosine of the angle. So we can generalize this and say that, x is always equal to r cosine theta, and y is always equal to r sine theta. And, now we have that x is, 5. X is always equal to, x in this case, is equal to 5. The cosine of 5 pi over 6 is negative square root 3 over 2. And then y is equal to 5 times 1/2. And so we get our coordinate become negative 5 square root 3 over 2, comma, 5 halves. And I wouldn't put this into a calculator or anything. I just leave it like here as a fraction. So now that's the polar coordinate system. There's so many more cool things you can do with this, but that's just the basics, and you're converting between rectangular and polar.